10 billion light-years wide. I want you to pause for a moment and let that number sink in. Not 10,000 miles, not 10 million miles, 10 billion light-years. A structure so vast that if light itself began crossing it when the first dinosaurs walked the Earth, it still would not have made it to the other side. And yet, according to everything we thought we understood about physics, gravity, and the age of the cosmos, it should not exist at all. The universe is 13.8 billion years old. That is the total time since the Big Bang. In that time, matter has been spreading outward, cooling, clustering under gravity, slowly forming stars, galaxies, and galaxy clusters. But there has not been enough time for gravity to assemble anything this enormous. The equations say no, the simulations say no. The standard model of cosmology says no. And yet when astronomers looked deep into space, mapping distant explosions billions of light-years away, they found a wall of galaxies so immense that it stretches across nearly 10% of the observable universe. If this structure is real, then something about our understanding of cosmic growth is incomplete. Something fundamental may be missing. Tonight, as you lie back and let your mind drift into the deep quiet of space, we will explore the largest structure ever discovered, a structure that challenges the limits of cosmic order, and gently unravel how the universe builds its grand architecture. Before we journey further into the cosmos, take a brief moment to support the channel. If you enjoy deep space documentaries designed to calm your mind while expanding your understanding, consider subscribing, leaving a like, and sharing your thoughts in the comments. And here is a simple question for you: from which part of the United States are you watching right now? Whether you are listening from the busy streets of New York, the deserts of Arizona, the forests of Oregon, or the quiet towns of the Midwest, leave a comment and let us know where you are drifting into space from tonight. Now, let us begin at the beginning, not with the structure itself, but with the universe that gave birth to it. The universe began 13.8 billion years ago in an event we call the Big Bang. It was not an explosion in space, but an expansion of space itself. In the first tiny fraction of a second, the universe underwent a rapid inflation, expanding faster than the speed of light. During this brief and extraordinary moment, quantum fluctuations, tiny ripples in energy at the smallest scales, were stretched across cosmic distances. These fluctuations became the seeds of all structure. After inflation ended, the universe continued expanding and cooling. Energy condensed into particles. Protons and neutrons formed. A few minutes later, simple nuclei like hydrogen and helium were created in a process known as Big Bang nucleosynthesis. For the first 380,000 years, the universe was a hot, dense plasma of charged particles and radiation. Light could not travel freely, it scattered constantly off electrons. Then, as the universe cooled further, electrons combined with nuclei to form neutral atoms. This moment, called recombination, allowed light to travel unimpeded for the first time. That ancient light still fills the cosmos today as the cosmic microwave background radiation, a faint afterglow that provides a snapshot of the universe when it was less than 1 million years old. In that ancient glow, we see slight temperature variations, differences of only a few parts in 100,000. Those small differences represent regions that were slightly denser than others. Gravity began to amplify these differences. Over millions of years, the denser regions pulled in more matter. Dark matter, an invisible substance that interacts through gravity but not light, played a crucial role. It formed a vast cosmic scaffolding, a web of filaments stretching across space. Ordinary matter, the atoms that would become stars and planets, fell into this dark matter framework. Over hundreds of millions of years, the first stars ignited. These stars gathered into galaxies. Galaxies merged and formed clusters. Clusters grouped into superclusters. When astronomers map the large-scale distribution of galaxies, they see something remarkable. The universe resembles a cosmic web. Vast filaments connect dense nodes of galaxies, while enormous voids, nearly empty regions, stretch between them. This structure is not random. It is the result of gravity working over billions of years on the initial seeds planted by quantum fluctuations. According to our current understanding, there is a limit to how large coherent structures can grow within the age of the universe. This limit is related to what cosmologists call the scale of homogeneity. On very large scales, the universe appears uniform. If you zoom out far enough, matter should be distributed evenly, without preferred directions or massive asymmetries. This principle is known as the cosmological principle. It states that the universe is homogeneous and isotropic on sufficiently large scales. It is a foundational assumption in modern cosmology. Computer simulations using the known laws of gravity, dark matter, and dark energy attempt to recreate the evolution of the universe from its early fluctuations to the present day. These simulations successfully produce a cosmic web. They form galaxies, clusters, and superclusters that resemble what we observe. But they also predict that structures larger than a certain scale should be exceedingly rare or effectively impossible within 13.8 billion years. And yet, as astronomers continued mapping distant galaxies, they began noticing patterns that pushed those limits. One of the most surprising discoveries did not come from traditional galaxy surveys, but from some of the most violent events in the universe: gamma-ray bursts. Gamma-ray bursts are brief, intense flashes of high-energy radiation. They are the most energetic explosions known, releasing in seconds as much energy as our sun will emit over its entire lifetime. Some gamma-ray bursts are produced when massive stars collapse into black holes. Others may result from neutron-star collisions. Because they are so luminous, gamma-ray bursts can be seen across vast cosmic distances. They act like cosmic lighthouses, illuminating regions of the universe billions of light-years away. Astronomers began cataloging the positions and distances of these bursts. Each gamma-ray burst is associated with a host galaxy. By measuring their redshift, the stretching of light due to cosmic expansion, scientists can estimate how far away they occurred. When plotted on a three-dimensional map, these bursts revealed something astonishing. Instead of being evenly distributed at the largest scales, a significant number appeared clustered within a particular region of the sky at similar distances. This clustering suggested the presence of an enormous structure, a wall of galaxies spanning roughly 10 billion light-years. To put that in perspective, our own galaxy, the Milky Way, is about 100,000 light-years across. The local group of galaxies, which includes the Milky Way and Andromeda, spans about 10 million light-years. The Laniakea supercluster, the vast region that contains our galaxy and thousands of others, stretches roughly 500 million light-years. 10 billion light-years is 20 times larger than that. It is not merely a supercluster. It is a structure of almost unimaginable scale. If confirmed, such a wall challenges the assumption of large-scale homogeneity. It suggests that matter may be organized into structures far larger than previously thought possible. Some scientists argue that what we are seeing could be a statistical fluke, an artifact of limited data. After all, mapping the distant universe is difficult. We see only a portion of the sky with enough detail. Gamma-ray bursts are rare events, and their distribution may be influenced by observational biases. However, the possibility remains that this structure is real. If it is, then we must ask how it formed. Gravity is the primary architect of cosmic structure. But gravity operates at a finite speed, limited by the speed of light. Regions of space that are too far apart cannot influence each other if light has not had time to travel between them. This concept defines the observable universe. We can only see as far as light has had time to reach us since the Big Bang. Within that observable universe, structure formation is constrained by causality. There has only been so much time for matter to collapse into bound systems. The larger the structure, the longer it takes to assemble. For a 10 billion light-year wide structure to form, matter across that entire region would have had to coordinate its collapse over timescales that appear too short given the age of the cosmos. One possible explanation is that the seeds of this structure were already present at extremely large scales in the early universe. If inflation produced fluctuations not only at small scales but also at very large wavelengths, then gravity could amplify those fluctuations over billions of years. In this view, the wall is not something that formed from scratch recently, but a natural amplification of ancient primordial variations. Another possibility is that our understanding of dark matter or dark energy is incomplete. Dark matter provides the gravitational backbone for structure formation. If its properties differ slightly from what we assume, perhaps allowing more efficient clustering on large scales, then larger structures could emerge. Dark energy, the mysterious force driving the accelerated expansion of the universe, also affects how structures grow. It counteracts gravity on large scales. If dark energy behaves differently over cosmic time than our models predict, the growth rate of structures might change. There are also more radical ideas. Some cosmologists have explored modifications to general relativity on large scales. If gravity behaves differently across billions of light years, perhaps becoming stronger or weaker under certain conditions, then our expectations for structure size would need revision. These theories remain speculative, but they highlight how a single observation can ripple through the foundations of physics. As we gently continue this journey, imagine floating above the cosmic web. You see countless galaxies glowing softly, connected by faint filaments of dark matter. Between them stretch immense voids, regions so empty that a spaceship traveling at the speed of light would drift for millions of years without encountering a single galaxy. And then, across a vast swath of space, you notice something extraordinary, a continuous chain of galaxy clusters forming a colossal wall, extending farther than any structure you have ever seen. It is not a solid barrier, but a region of enhanced density where galaxies are more numerous than average, forming a coherent pattern across unimaginable distances. To understand why this is so unsettling to cosmologists, we must revisit the cosmological principle. This principle underlies the equations used to describe the universe as a whole. It allows us to model cosmic expansion with the Friedmann equations, derived from general relativity. These equations assume that, on sufficiently large scales, the universe is uniform. If enormous structures violate this assumption, then the mathematical simplicity of our models may be an approximation rather than an exact description. Yet, it is important to approach such claims with caution. Astronomy often deals with incomplete data. When we observe distant regions, we look back in time. Light from 10 billion light-years away began its journey when the universe was much younger. We are not seeing the structure as it is today, but as it was billions of years ago. Additionally, our surveys cover limited volumes. Cosmic variance, the statistical uncertainty inherent in observing only one universe from one vantage point, can produce apparent anomalies. For now, allow your mind to rest on the vastness of it all. 10 billion light-years. A structure so large that it spans a significant fraction of the observable cosmos, a challenge not only to our equations but to our intuition. The universe has always surprised us, from the discovery that galaxies exist beyond the Milky Way, to the realization that the expansion of space is accelerating. Each revelation has expanded our perspective. Perhaps this immense wall is another step in that journey, a reminder that the cosmos is deeper, stranger, and more intricate than we ever imagined. As the stars slowly drift across the night sky above America, from the Atlantic coast to the Pacific shore, from the Great Plains to the Rocky Mountains, remember that every point of light is part of a vast interconnected web. And somewhere out there, billions of light-years away, lies a structure that may rewrite our understanding of how everything came together. In the next chapter, we will follow the trail of gamma-ray bursts more closely and uncover how these distant explosions revealed the impossible. Gamma-ray bursts, these fleeting flashes of extreme energy, lasting anywhere from milliseconds to several minutes, have become some of the most powerful tools for probing the deep universe. And it was through them that astronomers first glimpsed the outline of something that should not exist. Gamma-ray bursts, often abbreviated as GRBs, were first detected in the late 1960s by satellites designed to monitor nuclear activity on Earth. Instead of detecting terrestrial explosions, they recorded intense bursts of gamma radiation coming from deep space. For decades, their origin remained a mystery. Eventually, astronomers discovered that these bursts originate from distant galaxies, often billions of light-years away. Some are associated with the collapse of massive stars into black holes, events known as hypernovae. Others result from the merger of neutron stars, collisions so violent that they produce ripples in space-time itself. Because gamma-ray bursts are so luminous, they can be seen across enormous cosmic distances. A single burst can briefly outshine an entire galaxy. This makes them ideal beacons for mapping the far reaches of the universe. Unlike galaxies, which require long exposures to observe at extreme distances, GRBs announce themselves dramatically. Once detected, telescopes quickly turn to measure their afterglow across multiple wavelengths, allowing astronomers to determine their redshift and therefore their distance. Redshift is central to understanding cosmic scale. As the universe expands, light traveling through space is stretched. The longer the light has been traveling, the more it is stretched, shifting toward the red end of the spectrum. By measuring this shift, astronomers can calculate how far away a source is and how long ago its light began its journey. Many gamma-ray bursts have redshifts corresponding to distances of billions of light-years, placing them in the early epochs of cosmic history. As data accumulated over the years, astronomers compiled catalogs of GRB positions and distances. At first glance, their distribution appeared roughly uniform, as expected under the cosmological principle. But as the sample size grew, subtle patterns began to emerge. A significant number of gamma-ray bursts were clustered within a specific redshift range and within a particular region of the sky. When plotted in three-dimensional space, these bursts appeared to outline a gigantic arc or wall-like structure. This feature, often referred to as the Hercules corona borealis Great Wall, stretches approximately 10 billion light-years across. Its name reflects the constellations in which it appears when projected onto the sky. Although constellations are simply patterns as seen from Earth and do not represent physical proximity, the clustering of GRBs within this projected region at similar distances suggests a real physical structure in space. To appreciate the scale of this discovery, consider the comparison to other known large-scale structures. The Sloan Great Wall, discovered in galaxy surveys, spans about 1.4 billion light-years. Even that structure was considered immense and pushed the upper limits of expected sizes. The Hercules corona borealis Great Wall dwarfs it by a factor of several times. It is not merely larger, it challenges theoretical limits derived from our models of cosmic evolution. So how do astronomers determine whether such clustering is statistically significant? The key lies in careful analysis. Scientists divide the sky into regions and compare the observed number of gamma-ray bursts in each region within specific redshift intervals. If the universe is homogeneous on large scales, the distribution should be roughly uniform when averaged over sufficiently large volumes. Deviations can occur due to random fluctuations, but the probability of extreme clustering can be calculated. In the case of this massive structure, researchers found that the clustering of GRBs in that region was unlikely to be due to chance alone. Statistical tests suggested that the probability of such a concentration occurring randomly was small. However, the total number of observed gamma-ray bursts remains limited compared to the total number of galaxies in the universe. This introduces uncertainty. Small sample sizes can exaggerate patterns. Moreover, gamma-ray bursts are not perfect tracers of matter distribution. They occur in specific types of galaxies, often those undergoing active star formation. Their frequency may vary with cosmic time and environment. Observational biases also play a role. Telescopes have limited sensitivity and sky coverage. Some regions of the sky are observed more frequently or more deeply than others. Dust within our own galaxy can obscure distant sources in certain directions. Astronomers attempt to correct for these biases by modeling detection efficiency and comparing results with simulations. In computer simulations of the universe, cosmologists input the known laws of physics, initial conditions derived from the cosmic microwave background, and parameters describing dark matter and dark energy. They then allow the simulated universe to evolve over billions of years. These simulations produce cosmic webs, filaments, clusters, and voids that resemble observed structures. Yet when researchers search these simulations for structures comparable in size to the Hercules corona borealis Great Wall, they rarely find anything similar. Structures of that magnitude are extraordinarily uncommon within the standard model of cosmology, often called lambda cold dark matter. In this model, dark matter is cold, meaning its particles move slowly compared to the speed of light, allowing it to clump effectively. Dark energy, represented by the Greek letter lambda, drives the accelerated expansion of the universe. The growth of structure in this framework is a balance between gravitational attraction and cosmic expansion. In the early universe, matter density was higher, and gravity dominated locally, allowing structures to grow. Over time, as dark energy became more influential, expansion accelerated, suppressing further large-scale growth. This means that there is a window of time during which structures can form efficiently. Beyond certain scales, there simply has not been enough time for gravity to pull matter together into coherent formations. The existence of a 10 billion light-year wide wall suggests one of several possibilities. Perhaps the initial density fluctuations were larger on certain scales than we infer from the cosmic microwave background. Although measurements of that background, particularly from missions like the Planck satellite, show remarkable uniformity, there are small anomalies that continue to be studied. If the early universe contained subtle large-scale variations beyond what current measurements reveal, they could seed enormous structures. Another possibility involves cosmic variance. We observe only one universe from one location within it. Statistical predictions describe what is typical across many possible universes, but we have access to only one realization. It is possible, though unlikely, that our observable region contains an unusually large structure simply by chance. There is also the question of how we define a structure. The cosmic web is not composed of solid objects with clear boundaries. Instead, it consists of regions of higher and lower density. At some level, deciding where one structure ends and another begins involves thresholds. If we lower the density threshold, separate clusters may appear connected, forming larger apparent structures. Thus, part of the debate centers on whether the Hercules Corona Borealis Great Wall represents a single coherent entity, or a chance alignment of smaller structures along our line of sight. To visualize this, imagine looking at a distant mountain range through layers of fog. Peaks that are actually separated by valleys might appear connected from a particular vantage point. Similarly, galaxies that are not gravitationally bound into a single massive entity might align in such a way that they seem to form a continuous wall. Despite these uncertainties, the discovery remains provocative. It encourages astronomers to gather more data. New gamma-ray bursts continue to be detected by space observatories such as the Neil Gehrels Swift Observatory and the Fermi Gamma-ray Space Telescope. Each new burst adds a point to the cosmic map. Over time, as the sample grows, the statistical picture becomes clearer. Beyond gamma-ray bursts, large galaxy surveys provide complementary information. Projects like the Sloan Digital Sky Survey and more recent deep field observations map millions of galaxies across vast volumes. By comparing the distribution of galaxies with the GRB-derived structure, scientists can test whether the wall appears in independent datasets. There is also the subtle interplay between observation and theory. When a surprising structure is found, theorists revisit their assumptions. They explore whether modifications to parameters within accepted limits could allow such a structure. They test alternative dark matter models, such as warm dark matter scenarios, in which particles move faster and suppress small-scale clustering but might influence large scales differently. They examine whether non-Gaussian initial conditions, meaning deviations from the simplest statistical description of primordial fluctuations, could produce rare superstructures. At the same time, observers refine their techniques. They improve redshift measurements, correct for selection effects, and search for additional tracers such as quasars or galaxy clusters in the same region of space. Science advances not by clinging to anomalies nor by dismissing them, but by patiently testing them from every angle. As you continue to relax and let your thoughts drift across the universe, consider the quiet persistence of the scientific process. Somewhere in a control room, a satellite detects a brief flash of gamma radiation. Within seconds, automated systems calculate its position. Telescopes around the world swivel to capture its fading afterglow. Spectra are recorded. Redshift is measured. Data are uploaded, cataloged, analyzed. Each burst is a tiny piece of a grand cosmic puzzle. And slowly, from these fleeting explosions, a picture emerges of something immense. A wall of galaxies stretching across billions of light years. A feature that whispers that the universe may still hold surprises beyond our current understanding. Whether it ultimately reshapes cosmology or settles into the statistical fringes of expected structure, it reminds us that the cosmos is not a static story. It is a living investigation unfolding across time. If science and the vastness of space captivate you, then your place is right here. Subscribe to The Boring Universe and come closer to the cosmos with every new video.